So can everybody see the slides and the transition of the slides?
Yeah.
Okay, great. Hopefully today it is working well. All right. So I think we should start. Okay, so first of all, just a reminder, this Friday will be the due of our homework 1. So if you still haven't started doing the homework 1, please start as soon as possible and take advantage of the Piazza forums and office hours. I've seen a lot of interactions on Piazza. That's really good. Right? Keep utilizing those platforms. And also, please think about what kind of course project you would like to do, right? Exploratory or Kaggle, right? And team up and write down documentation and send to and upload your project proposal to the Canvas in time. Okay, so today we're gonna talk about a new type of machine learning methods. It's called ensemble learning. Right? So I remember previously we talked about decision trees, right? That's about our first specific machine learning algorithm as a single model, and ensemble learning, as we'll say, is about a collection of weak models. How do you smartly combine them to get a very strong classifier? So the most important learning algorithm in ensemble learning include boosting and bagging. So we're going to introduce them one by one. Right? We're going to first today we're going to introduce the formulation of boosting. Right? And you see that it was proposed based upon a theoretical question in computational learning theory. So see that why theory is important, right? Although we're not gonna explore in depth about theory in this class. Right? And then we'll introduce this main focus, right? We'll introduce the most popular and successful boosting algorithm called Eta Boosting. Right? Everyone will be requested to implement your own Eta Boost. And finally, we'll talk about bagging methods. Bagging is actually is really straightforward, but we can justify them in theory as well. Right? So first, let us look at what is boosting. Right? How do we formulate the problem, the boosting learning algorithm? So boosting, in general, is a learning approach to construct a strong learner given a collection of weak learners. Right? Of course, in theory, to derive some kind of bound, to give some theoretical guarantee, you might they might think of possibly infinite number of weak learners, but in practice, we'll always have a finite number of weak learners. So historically, the proposal of boosting algorithm is an answer to a theoretical question in impact learning. So this is the seminal work, the paper published by Robert Shapiro in 1989. A first time talk about the strengths of weak learnability. So what does it mean? It just means that, okay, suppose I have a bunch of weak learners, right? We call it rules of thumb, whatever. You can for concrete uh, instances, you can consider a decision tree is a very shallow, a narrow decision tree. Perhaps it only has um, one one node to split data set. It's called decision stumps, right? Oh, someone said the slide stop. Is it working? I'm right now. I'm trying to move the slides. Do you see the transition?
Yes, it's working now. It just wasn't working, I guess, for the first few minutes.
Okay, okay. So happy it gets back to normal, right? Oh, so let us continue, right? So boosting essentially is a way to leverage a set of such rules of thumb to create a much stronger classifier, which can be stronger than any individual uh, strong classifier. So, so it is ensemble method for sure, a class of learning algorithm that composes classifiers using other classifiers as building blocks. So you can view like other classifier as kind of a brick, right? You use those bricks to build a house. This is this is the key of ensemble learning. Right? And boosting has amazing theoretical guarantees than other ensemble methods. That's why we're going to first introduce boosting. So and boosting algorithms have been used successfully used in numerous applications, right? So the first one is the face detector. This example actually we have covered uh, at our first lecture or second lecture. We talk about the applications of the various applications of machine learning, right? So nowadays, if you use digital camera or you just use your cell phone to take pictures, right? So there is oftentimes you can say like once some human beings show up in your camera, there's a there are often some like green boxes, right? Bound bound their faces, right? So they're quite accurate, and when people move in, the bounding box will move as well, right? So this face detector um, is mostly built upon the Eta Boost, which we're going to discuss in detail today. Yeah, boosting is one technique under ensemble learning, right? As we just mentioned, right? Ensemble learning has two major approaches. One is called boosting, the other is called bagging, and we're gonna first introduce boosting and then bagging. And other applications include handwritten letter recognition, right? It's very important for uh, mailing, right? So when you send out letters nowadays, like the address and also the postcodes will be first will be automatically recognized by machine learning algorithms by boosting or by other like neural network, whatever. Only for those um, not for those unclear writings which cannot be recognized by automatic algorithms will be delivered to human, and they will see it by with human eyes, right? And text classification, news tagging, information retrieval, motion capture, DNA sequence analysis, and a lot, right? So basically, boosting is a framework that is both theoretical sound and also working very well in practice. So what is the formulation of boosting, right? So here we just give a formal definition of boosting. Although in practice, people don't care about that, but you need to know a kind of more rigorous definition in computational learning framework, right? So that connects to what we have discussed in last week, right? Pack learning, right? So we talk about the pack learnability, right? So we say that if an algorithm can pack learn a type or family of target functions or concepts, right? We call this algorithm is really good, right? Because it's a strong requirement. We require the algorithm can, for any distribution over the instance space, for any designated error level and confidence level, we only need a polynomial many random training examples, sample from the data distribution, right? It can have a very high chance to find a hypothesis with small generalization error, right? How small is the error is less than or equal to epsilon, and how high the chance is at least 1 minus delta. So we call such a learning algorithm as a strong pack algorithm. So, but someone asked, right? I mean, in practice, it's really hard to find such a strong pack algorithm. It seems this definition is impractical. Right? It only has some like theoretical meanings, right? And is there any weaker definition and which can guide our practical learning practice, right? And yeah, it is, right? We call this type of algorithms called weak pack algorithm. So what kind of algorithm can be called weak pack algorithm? It satisfies all the requirements of the strong pack algorithm, except that we do not have a strong requirement for the true error. We just require that your true error is slightly better than 50%. So you can say epsilon is no less than half minus some value gamma, right? The gamma is a small value, right? You can designate like 0.01, 0.05, whatever, right? So basically, the meaning is that, okay, if for any distribution over the instance space for every confidence level epsilon, and an algorithm can use a polynomial many training examples, right? Can find a hypothesis with high chance to find a hypothesis whose true error is slightly better than random guess. Okay, this is just slightly better than random guess. The random guess just give you 50% accuracy, right? It's slightly better than a random guess, and then we can call this algorithm as a weak pack algorithm. Right? So, and then given, you can imagine that a lot of algorithms are kind of weak pack algorithm, right? And it's pretty hard to find a strong pack algorithm because it's too strong. It's so expressive, right? So the question, a natural question arises, right? So does weak learnability imply strong learnability? Meaning that if we have a weak pack algorithm for concept class, meaning a type of target functions, right? Is this concept class also learnable in a strong sense, meaning that if there some kind of strong pack algorithm, right, which can learn, which can very well learn every target function in the concept class with strong guarantees. And if so, how is it possible to construct such a strong pack algorithm based on a set of weak pack algorithms? So that's where that's how this boosting framework was formulated. It arises just from a theoretical question. So here I just want to share with you a brief history about the development boosting algorithm. So in 1989, Robert Shapiro is actually the pioneer about the invention of Eta boosting algorithms. Right? So he proposed the first provable boosting algorithm, and he called the weak learner 3 times on 3 modified data distributions, and it turns out that his boosted learner can get slightly improvement in accuracy, and they apply this algorithm recursively. But although it is kind of theoretical sound, um, the practical performance is not that good. And later, Froome in 1990s, he proposed a so-called optimal algorithm that can boost by majority, which we'll see later what does it mean by boost by majority. And then And in 1992, these three researchers, they conduct experiments, use boosting, and their algorithm is also limited by practical drawbacks. And the breakthrough was made in 1995 by Froome and Shapiro, and they introduced the Eta Boosting algorithm, which we're gonna discuss today. So uh, the Eta Boost not only enjoys the theoretical advantages, but also exhibit strong practical advantages over previous boosting algorithms. So after that, like numerous extension applications of Eta Boost um, showed up. And right now, like Eta Boost is often used like one of the strongest machine learning classifiers in practice, and was used everywhere. Right? So the inventor, um, Froome and Robert Shapiro, they were awarded a Goldel Prize in 2003. This is kind of like top award in theoretical computer science. So now we have introduced the formulation of boosting. Right? Any questions so far? We're going to discuss about one detailed algorithm. So before we proceed, any question regarding the conceptualization of the boosting and the intuition?
Yeah, I have a quick question. So are you saying that the boosting algorithm is a strong pack algorithm?
No, the goal of boosting algorithm is to achieve a strong pack algorithm. But whether it is really strong pack algorithm is really determines is determined by the family of the concepts you want to learn. Right? I mean, even Eta Boost, it cannot guarantee for any type of target functions it is packed. It's probably approximately learnable.
Okay, so this is just a way to kind of classify the algorithms in the future as we start looking into this more, essentially.
Yes, this is a way. I mean, from theoretical sense, right? We want to build a path onto that, right? This theoretical question, like whether we can derive strong pack algorithm from weak pack algorithm, stimulates the development of Eta Boost or invention of Eta Boost. Sure. And there is some kind of theoretical guarantee, like for some human-made type of concepts. Yeah, they show that Eta Boost can pack learn that, but
cool.
In practice, there are a lot of problems, right?
Right. Okay, I see what you're saying. Thank you.
No problem. So any other question? We need to ensure we're on the same page. Okay, great. So now let us look at some detailed things, right? We're going to introduce Eta Boost, the most successful boosting algorithm so far, and a lot of variants on that. And we're going to introduce the intuition of Eta Boost and algorithm details and why it works. And we'll see some kind of like a counterintuitive results Eta Boost. You'll see that Eta Boost is usually not suffer from it does not suffer from overfitting. Okay, so to illustrate the algorithm details, we'll use a toy example. Like suppose our task is to classify the points in this rectangle, right? So we have like 10 training examples, positive and negative, labeled here, right? So we'll build a strong classifier by weak classifiers. So our weak classifiers are just two types. One weak classifier is just a horizontal line, meaning the line parallel to the x-axis. And the other weak learner or weak classifier is just a vertical line parallel to the y-axis. So the difference between weak classifiers is just where you place the horizontal line, right? You can put it here, you can put it here, right? The position. And similarly, you can put the vertical lines here, here, and here, right? So we just need to choose different positions on x-axis and y-axis to find the good weak learners. Right? So initially, we treat all the examples as equally important. So as we will see that when we learn more and more weight classifiers, we're actually dynamically adjusting the weights or importance of each training example. But at the beginning, we just assume all the examples are equally important, meaning that they have the same weight. So first of all, we try to find a weight learner, a weight classifier, each one that can give the best performance in training data. So each one is the best classifier on this data. So it turns out that each one is a vertical line, right? And it is placed when it is placed here, we got the best training accuracy. And then we should look at how much error it does, right, in predicting the training examples. So how many examples did H1 fail to predict?
Three.
This three, right?
Yep.
There are three positive examples. They're on the right hand side, right? So each one will give like incorrect prediction on these positive examples. They predict them as a negative, right? So actually we have three mistakes made by H1. So our error is 0.3, right? Why? Because we have 10 training examples in total, and H1 misclassified 3 of them. So the training error in the first one is 0.3. Is that good? Is everybody is everybody feeling okay with that? Is our setting right? Okay, I assume everybody is satisfied with the current stage, right? So we finished our first round of learning. We find the first. Oh, someone asked. So we are looking for a purity of the best classifier. Um, uh, yeah, you can view it in that way. Yeah, I'm happy that you connect this to decision trees, although it's not necessary. Yeah, you're right. So actually, we're looking for a classifier which can give the best prediction accuracy. Well, that means after prediction, your purity arrives at your purity should be highest. But it does not mean that you have like 100% purity. That means you have 100% accuracy. Any other question regarding the setting? This very first step, our first round of learning in the boosting framework. Okay, so after we have learned our hypothesis or the weight classifier, right, and according to the mistakes each one has made, we're gonna adjust the weights for the training examples, meaning that we want to increase the importance of the examples with mistakes and downweight the examples that each one correctly predicted. So see that here we made 3 mistakes, right, with H1, and then we're gonna increase its weights. So you can see the size is enlarged, right? Just representing their weights are enlarged and they're more important. At the same time, we kind of shrink the weights for the correct predict examples. Why? Because in the next round, we want to prevent the same mistake made by H1 again. That's why we will those misclassified training examples in the previous round to be more important. Meanwhile, because the remaining examples have already been correctly classified, right? So they are not that important. So we're gonna downweight. We're gonna downweight them. Okay. So this is the key idea. So now, based on those reweighted training examples, we're gonna find a second a second weak classifier, which can give you the smallest error. And here the error will be the weighted error, rather than just count the number of misclassified examples divided by the total number of examples. Not that it's a weighted error. So obviously, associated with the next round of learning is a set of weights. Right? We denote it by dt. So dt is a collection of the sample weights, right? One for each example, indicating how much should the weak learner at this round care about this example. Right? So the larger the weight in dt, the more important the new classifier will view those examples. Right? So now we find a second weak learner, H2, right, which is also a vertical one, right? It's a vertical classifier. And turns out that the best position is on the right, right? So obviously, from the classification results, H2, a classifier learned on this data, still makes 3 mistakes, right? But now, the error is no longer 0.3. It becomes 0.21. So I want to ask why. Can anyone give me give some like explanation why the error now is decreased to 0.21 rather than 0.3?
Because these negative examples were downweighted.
Yes, exactly, right. Well, I don't know, Spencer. You wrote the equation on that. I don't know if it is true or not, because it really depends on the sample weights, right? But the idea is correct. So basically, after the previous round of learning, we have downweighted those examples because they're all correctly classified by H1 in the first round, right? So we don't view them as that important. We downweight them. So now, in the second round, H2 correctly classify those misclassified examples in the first round, but misclassify those examples which were correctly classified in the first round, right? That's why we got a smaller error, so 0.21, right? And in general, how do we compute the weighted error? Right? So here's the formula. We just need to go through all the training examples. And Jared, I'm going to answer your question after we talk about the definition of the weighted error, right? How we compute the weighted error. So epsilon t is computed by subtracting half times a summation over all the training examples, where each summand is the weight of the training example, multiplying with the product between the ground truth label and the predicted label. Okay. So if you want to calculate the weighted error of your learned hypothesis or weak classifier, you just apply this formula, right? So now I want to say why this is reasonable, right? So we need to look at the cases where we make correct prediction and we make wrong prediction, right? So actually we have two cases, right? So first, when your prediction is different from when your prediction is different from the ground truth, what is the product of this yi h of xi? Any thought? What if your prediction is wrong? Like, what is the value of yi times h of xi? Any guess?
0. If yi is 1 and hxi is 0, then uh, it's wrong. So multiplication would be 0.
Oh no. So we assume that your prediction is always 1 or -1. There's no 0.
Okay.
So then
But
if it's wrong, it'll be negative.
it will always be negative.
Yeah. So actually, we'll see that if your prediction is incorrect, then this product is always -1. Right? Consider that yi is positive, but the prediction wrong will be negative, right? 1 times -1, right? If your yi, the ground truth is negative, meaning -1, and you make a wrong prediction, then you give positive prediction, then h of xi will be 1, right? Multiplying together ends up with -1 as well, right? So as long as you make wrong prediction, this product will always give -1. If you make correct prediction, of course, you'll give +1. So now we can see if you make a correct prediction.
Sorry, I think there was some confusion about what the variables were in the equation. But so y is what you are predicting it is, and h of x is what it is.
Yes, yi is the label, the ground truth label, -1 or +1, and h of xi is our prediction, is also 1 or -1.
Gotcha. And then dt of I, that's the weight.
Yeah, that's the weight. That's the weight of example I in wrong t.
Awesome. Okay, thanks.
Yeah,
Sorry for
that's the definition here, right? dt is a set of weights at wrong t, right? One for each example. So now, given these two cases, right, we can see that if we make a correct prediction, right, so this product will end up with being 1, right? So actually subtracting half by half of this correctly, the weight of this correctly predicted example, right? If you make a correct prediction, or you make a wrong prediction, and then this becomes negative, right? So this is -1, two negatives become positive, right? So after adding half of the weight for those incorrectly predicted examples, if you combine them together, you can derive that epsilon t is actually the summation of the weights of all the incorrectly predicted training examples. So now this is much more reasonable, right? So this is weighted error. We just look at which examples are misclassified, right? And we just add up their weights. This is weighted error. But regarding how you derive from this to this, I will leave it an exercise for you. I highly recommend you to do this exercise because it's very likely to be included in next homework. Right? And also by doing this simple derivation, you have a better or more understanding about this definition of weighted errors and how those weighted errors can, how the examples weights can affect the error. Okay. So now going back to Jared question, right? So are we finding the best vertical line while some anonymous classifier algorithm? Yeah. So right now I kind of like ignoring how you train a weak classifier. We assume that the algorithm is there. You have some library and you just call that algorithm to feed those weighted training examples to that library. It can automatically give you such a weak classifier. Learn on this data. Right? Because we're talking about ensemble learning, right? Ensemble mean that okay, I have some like stable and stable but weak learning algorithm which are ready to call anytime, right? You just need to call that algorithm multiple times to generate a collection of weak classifiers, and then the key is how to combine them together. Okay, any questions so far? This is about how we compute the sample weights based on the prediction of our learned hypothesis. Not sample weights, the weighted error. Okay. So now, based on those sample weights, we can derive that, okay, the weighted error for the second classifier, H2, is 0.21, right? So again, for the next round, to proceed to the next round, we're gonna adjust the weights of those training examples again, meaning that we're gonna increase the weights for those misclassified negative examples, right? And then we downweight those correctly classified examples by H2, meaning that those examples, their weights will be decreased. So we end up with the training set for the third round. So we're gonna this is so we have H1, H2, and right now after the adjusting of the sample weights, we're gonna find a third weight classifier H3, right? So it turns out now we have a third classifier, which is a horizontal line, right? This is the position where is where you can get the best performance, right? So now we should look at how many mistakes H3 made to predict the training examples, right? So you can see right now we still have 3 misclassified examples, right? But now, because of the different sample weights, right, we have the weighted error to be 0.14, because those 3 misclassified examples, their weights will shrink, and if you add them together, it ends up with 0.14. And if the computation of this weight just follow this. Any questions so far? So everyone is good, right? Okay. So now suppose we stop creating new classifiers. We just end our boosting algorithm after 3 rounds of learning, right? So now we have collected 3 weak classifiers, right? 2 vertical lines, 1 horizontal lines, right? We want to combine them together to generate our final hypothesis. How can we do that? A straightforward way is just to perform a linear combination, right? We just do a linear combination of the predictions made by H1, H2, and 3, and the weights of those combination are denoted by alpha 1, alpha 2, and alpha 3. So in other words, we can view those alpha 1, alpha 2, alpha 3 as volts, right? So the volt for H1, alpha 1, volt for H2, alpha 2, volt for H3, alpha 3, right? And then you just add them together, you end up with the volts for positive labels, positive predictions, and the volts for negative predictions, and then just look at which prediction beats the other. Right? Then you give the final prediction. So those par example just illustrates the whole working procedure of the Eta Boost learning algorithm. So now we give outline of the boosting algorithm. So suppose we have collected a set of m training examples, x1, y1 to xm, ym, and where each instance xi is labeled by yi, who is either -1 or +1. And then we're gonna conduct big T iterations or big T rounds of learning, right? In each iteration, we first construct a set of sample weights, dt, on M training examples, meaning that we're gonna adjust the weight for each particular training example. And based on those weighted training examples, we find a weight hypothesis HT such that it has a small weighted error epsilon t. So after big T rounds of learning, we have collected big T weak hypotheses, right? And then we combine them, meaning through linear combination, to construct a final hypothesis denoted by H final. This is the whole algorithm framework. So any questions so far? Is everybody good?
So X is the feature and Y is the label?
Yes.
Okay, and that can be expanded, I'm assuming, to multiple features? Or...
Yeah, xi you can view it as a vector. It's a feature vector. Any other question? But intuitively, right? I want to emphasize the intuition behind this algorithm framework. So this is a sequential iterative algorithm, right? So in each iteration, we're kind of amplify the importance of those misclassified examples in the previous rounds of learning, right? And they want to find a new hypothesis which can better deal with those hard training examples, right? So at the beginning, every example is viewed as like equally important, right? And then every time you're gonna you're gonna make some mistakes by the current hypothesis, right? In the next round, we want to improve the previous learner by correctly classify those misclassified examples in the last round, right? So we hope that through this sequential procedure, we're gonna better deal with those hard examples to classify. And if we combine them together, we expect that our final hypothesis, our final classifier will be much stronger. Someone asked, are we learning alpha values or are they hyperparameters? Yeah, that's a very good question. So we're going to talk about like how do we calculate alpha values, how do we update them. But right now we just want everyone to be on the same page about this algorithm framework, and also appreciate the intuition behind that. Okay, so assume everyone is satisfactory, right? Yeah, negative wrong and positive right. Yes, and negative is just doesn't mean wrong. It just means okay, your prediction is negative example, right? And positive mean that okay, your prediction is positive example. Okay, so then the remaining details are how do we construct the sample weights, right? And how do we combine the final hypothesis, right? We know that we do a linear combination, right? But how do we identify the votes alpha 1 to alpha t, right? How do we calculate that, right? And also, yeah, and here, like after each round, how do we adjust the sample weights, right? So next, we're going to talk about the details about these two key steps. So first, how do we construct the sample weights? So here's the setting. We have M training examples, and we denote dt, denoted by dt, the set of weights over the examples. So dt1 meaning the weight for the first example in round t or iteration t, dt2 weight for the second example, dtm weight for the mth example at iteration t, right? So we want to adjust the sample weights so that at every round, the weak learner will look for hypothesis HT that emphasizes examples that have a higher DT rate. So initially, right, because we do not have any prior knowledge about each example, which example is important, which example is not important. So we will assign a uniform distribution over the examples, meaning that each weight is simply 1 over m. M is the number of training examples. So after T rounds, we will have DT and hypothesis HT that was learned. Right? And we also can calculate the error, the weighted error, epsilon t, that the learned hypothesis predict the training examples. Right? So for the T+1 round, we can find a hypothesis so that examples that were incorrectly predicted by HT are now correctly predicted by the new hypothesis, HT+1. To do so, we need to increase the importance of the misclassified examples and decrease the importance of the correctly predicted ones, right? So that means the adjusting of the sample weights is just to increase and decrease the corresponding examples. Right? So there are definitely a variety of approaches to adjust the sample weights to deliver those kind of flavors, right? But here we're going to focus on Eta boosting. Right? Eta boosting use this multiplicative way to upweight or downweight the samples. So basically, given dt and the hypothesis h of t in iteration t, right, we create dt+1 as follows. So first, if yi is the same as h of t xi, meaning that your prediction is correct, then we're going to multiply the previous weight dti by this e to the power of minus alpha t. So alpha t is some value we're going to discuss later, but alpha t is positive. So e to the power of minus alpha t is less than 1, right? Meaning that you're multiplying the previous weight by a value between 0 and 1, you actually decrease the weight, right? And if your prediction is wrong, then you time the previous weight by e to the power of alpha t. So alpha t is positive. E to the power of alpha t is positive 1, is bigger than 1, meaning that, okay, you amplify the weight, right? You amplify the sample weight. So if we summarize the two cases together, right? Because if you just consider two cases separated, it's kind of like inconvenient, right? We can summarize the updating of this weight using one formula. We just multiply the previous weight dti with this exponential factor, which is exponential to minus alpha t times the product between yi and the prediction ht of xi. Right? Why? Why can we do this? An idea?
The same as in the previous example where we have the negative and positive, that if they're both negative, then they'll cancel out and be positive. So we can consider that correct.
Yes, exactly, right? We just want to remind you, right? So this trick is used all the time. Right? We'll discuss about this. We will use this later when we talk about linear classifier, when we talk about small vector machines. They all use this kind of like to determine if you are making correct prediction or not, right? So remember, if your prediction is correct, then this product is always 1, right? So meaning we go back to this case, right? We go to this case, we're downweighting the example, right? Otherwise, if you make wrong prediction, this one becomes a -1, right? Negative becomes positive. So end up with this case, right? You're upweighting the example. So we can say, okay, in the first case, if you correctly predict example, you demote the correctly predict example. Otherwise, you promote the importance of the incorrectly predicted example. Right? So now how about ZT? Right? So ZT is just a normalizer. ZT is just to ensure that the summation of all the sample weights is 1. So it's just like distribution. It's just like a discrete distribution over all the training examples, right? You need to ensure their summation is 1. Yeah, someone asked ZT, right? So is YG in the HT binary values? Yeah, it's binary values, but it's not 0, 1. It's -1, +1. And it's just to ensure that you can use this trick to conveniently update the sample weights. So any questions so far? Okay, so then the remaining thing is how do we compute alpha t, right? So alpha t is computed from the weighted error epsilon t. So we just take a logarithm of 1 minus epsilon t over epsilon t and multiply it with half. We end up with alpha t. So remember epsilon t, which is weighted error, right? We're using some meaningful classifiers. That means the weighted error is less than half, right? If the weighted error is bigger than half, then we'd rather even use the random guess, right? So the value of alpha t will be bigger than 0. Because 1 minus epsilon t will be bigger than epsilon t, right? So this fraction will be bigger than 1, and you take a logarithm, it's positive, so alpha t is positive. And now, according to epsilon t, according to the previous sample weights, we can update the sample weights for the next iteration, right? And this alpha t is not only used to adjust the sample weights in each iteration. This alpha t also serves the vote for the final combination. So this alpha t, there's no confusion of the notation. This alpha t corresponds to previous alpha t we have just mentioned. Okay. So now I have addressed how we conduct the first step, right? How we construct distribution dt on the training examples in each iteration, right? And then next we're going to construct the final output H final, right? So remember, in the previous discussion, we talked about how to compute alpha t, right? It is based upon the weighted error, right? Just calculate logarithm 1 minus epsilon t over epsilon t multiplied with half, you get alpha t. You use alpha t to downweight or upweight the training examples in the next round, right? And those alpha t's are also used to combine the hypothesis to give the final prediction. So how do we make prediction at the final stage? We do a weighted combination, a linear combination of the prediction of each individual hypothesis. Okay? And then we take a look at sum. Why? Because each h of t x either gives a positive prediction 1 or negative prediction -1, right? So you add them together, you're actually computing their votes, right? Their votes are determining your alpha t, right? So if you end up with positive value, right, of this guy, then that means the total vote of the positive prediction beats the total votes for negative prediction. So you're going to give a final, you're going to give a +1 as your final prediction, right? And vice versa, right? And vice versa. And that means otherwise, if it is negative, means that okay, your total vote for the negative prediction dominates the total votes for the positive prediction. So you end up with a negative value, so your final prediction will be negative. Okay. So any questions so far?
Yeah, so for the alpha t, the alpha t is per iteration, right? Like you calculate it based on the error of that iteration?
Yes, exactly. Here.
Okay. Got you. So like, okay, so we have our classifier make a guess, right? Or, do its work and say, here's where I'm splitting it. then we calculate the error of that, right? Then we get alpha t, and then we weight based on alpha t, and then give its vote the weight of alpha t.
Yes, yes, exactly.
Okay, awesome.
Yeah.
Cool.
So later we'll look back again about all the algorithm steps, right? Because everybody, you will be requested to implement your own Eta boosting, right, based upon decision trees. Okay, any other questions about the algorithm steps? Great. So now let us look at the full algorithm, right? And which will be your blueprint to implement your own version of Eta Booster. So again, we assume like we have a set of M training examples where each instance is labeled by either -1 or +1. Right? We have to set the number of iterations, which is some kind of parameter to tune. Right? So initially, we'll set all the sample weights to be uniform, so 1 over M. And then we go through big T iterations. Inside each iteration T, small t, right, we're gonna find a weight classifier HT whose weighted classification error. So the weighted classification error is computed based on the sample weights, right, rather than just calculate the naive fraction of the errors. Right? So it's better than chance, meaning that your error must be the weighted error must be less than half. Right? And then we compute its vote. So alpha t, right? It's just the formula we just mentioned, right? And then according to alpha t, we update the values of the weights for the training examples, right? So we use this unified formula, right? We simply multiply each the previous weight for each training example by an exponential scalar to minus alpha t yi ht of xi, right? So this the value of this or the sign of this actually indicates whether you make correct prediction or not, right? If you're making a correct prediction, this is 1, and then your scalar is less than 1, you're down weighting, right? Otherwise, if you make wrong prediction, this one is -1, so minus positive, you're actually multiplying a scalar bigger than 1, you're promoting the importance of this misclassified example, right? And once you finish the multiplication and you just normalize them, you get ZT to ensure that the summation of all the sample weights in the new iteration to be 1. And then you just get to go to the next iteration, and then based upon the current sample weights, you find a new classifier. Hopefully you can correctly predict the misclassified examples in the previous round and to improve the performance, and you do it again and compute the votes and reweight the training example again until you finish all big T iterations. And finally, you have collected big T weight classifiers. You combine them according to their votes, right? You get the final hypothesis. So obviously we didn't specify like which weight classifier should we use, right? But most often we're going to use decision trees and shallow decision trees like decision stumps. So we actually mentioned decision stumps when we discussed ID3 algorithm, right? Decision stump is just one level decision tree, meaning that it will only select one feature to split the data. Okay, so now let us go back to the toy example. We discussed before, right? So we have 3 weak hypotheses, right? 2 vertical lines and 1 horizontal lines. We have their votes after 1, after 2, after 3, right? So you can see that all those classifiers are kind of simple. They have like a classification boundary parallel to x-axis, right? But if we can combine them together, if we look at the classification boundary again, it becomes much more complex, right? So this boundary can well separate all the training examples from the test examples. So now you can see, actually, even we only have a collection of simple examples. By smartly combining them together, we can still end up with a very complex and expressive classifier. So any questions so far?
Yeah, I have a question
Mhm.
about the votes, the alpha values. So what is that exactly? So like when you show it visually on the next slide, what does that mean in terms of like when we're weighting the different classifiers? Is it essentially saying how confident we are that that classifier is doing its job?
Yeah, you can view it in that way.
Okay, because like we're still, so if you go to the next slide and then one more, and when you show this picture, like we're going to get this same, we're going to get that same division independent of the alpha values, right? Like the alpha values are essentially representing, you're saying it's like a vote, so it's like it's essentially like confidence that this is a good, like on each of the classifiers, but ultimately that's not going to influence, like we're still going to have the same classifiers, right? I don't know if that makes sense. Like,
Let us put it in this way, right? So if you can take a look at any chain examples at this line, right? So
yeah,
actually you have predictions from H1, H2, and H3, right?
right.
And finally you see that H1, the prediction here made by H1 has the largest vote. That's where all those classic boundaries are still aligned with H1, meaning that it just means that the prediction made by H1 end up with the largest vote, meaning that okay, either H2 has aligned prediction with H1, or H3 has aligned prediction with H1, or just alpha 1 is bigger than alpha 2 or alpha 3.
But I guess like what does that mean in terms of like what does alpha represent in terms of like the result of the algorithm? Like I guess like it just seems like they're kind of helpful in basically expressing how confident it is, but that maybe I just need to hold on and wait and see what as we go into more detail with it and whatnot, it'll make more sense.
Yeah, so basically, yeah, I want to give a concrete example. Like, suppose H1 for a particular example, say here, right? H1 might give a prediction as positive, H2 positive, but H3 might give negative. And how can we determine finally we're going to predict this label as positive or negative?
Okay.
Yeah, we have an alpha 1 vote from H1's prediction. We have alpha 2 votes from H2's prediction. That means, okay, our positive prediction will end up with alpha 1 plus alpha 2 votes, right?
Okay. So it's going to help in terms of classifying, like once we've built this H final, then
Yes.
the alpha values are going to help determine like essentially like in evaluating test cases.
Yes.
Okay.
And
Okay.
yeah,
That makes more sense.
so you combine them together, and finally you're gonna like count how many votes the positive prediction will have, like come from all
Right.
the predictions, right? And how many votes negative examples come from. Just compare with them.
Okay. Sounds good. Thank you.
Okay.
I have one question before we move on. So when we have these H1, H2, and H3, are we so like let's suppose that our classifier is a decision tree. We're storing that decision tree for later use essentially because we're gonna if we get a test example, right?
Mhm.
Then we want to give that test example to H1 and give it to H2 and give it to H3, right?
Yes.
Okay.
Yeah. Of course. I mean, this is just conceptually how do you combine them, but in actual prediction, you're gonna feed the same example to all the H1, H2, H3, H big T, whatever, and then you just combine the prediction together.
So I had a question. So for this current example, we can have like, how do we propose H1? Like, so we have to start, H1 can have infinite number of possibilities on a real scale. So how do we like start that, come up with the H1 hypothesis? Are we
Yeah,
going
that's
to
a
discuss it
yeah
later?
that is assume that you have a learning algorithm which can give
Okay.
you which can learn each one,
Okay.
like decision
And-
tree, or
okay.
or some kind of horizontal or vertical classifiers.
Okay. So we know how to learn a weak classifier.
Yeah,
So
yeah, that's the
okay.
basic assumption. And we assume that okay, you have some weak learning algorithm, and whatever data you give it, it returns your hypothesis.
Okay. And this will actually like, as in decision trees, it will perfectly fit the training example. Like if we make it run for an infinite number of times on a data set, uh, this will also give us a training error of 1, will it?
Yes, yeah, that's a very good point, which we're going to discuss right now.
Okay.
So actually, there is some kind of theory about the training error, right? So intuitively, we can imagine that when we train more and more iterations, right, we will collect more and more weak classifiers, our training error is keep decreasing, right? But is it possible to get zero training error? The answer is yes. So here's the theorem. Um, suppose we run Eta Boost for big T runs, right? And let epsilon T to be half minus gamma T, right? So it's just uh, indicating, just emphasizing that epsilon T, just emphasizing that those are weak classifiers. It's just slightly better than the random guess, right? So if we take the lower bound of all gamma T's, we can show that the training error of the combination of this T, big T, weak hypothesis is upper bounded by this guy, which is an exponential term to the power of -2 gamma squared big T. So if I have a constant lower bound gamma, right? So obviously, when we increase the number of iterations, the training error will be decreased exponentially fast. So imagine that you run Eta Boost for 1,000 rounds. So obviously, you can imagine, okay, the training error will decrease to zero very fast. So we list the proof on our course website, right? So I suggest everyone to take a look at that. So the proof is not that hard. It's kind of like tedious. It takes one page, right? But it's simple. It doesn't require like any in-depth knowledge. Just some like uh, simple inequalities, those kind of stuff. But I hope everybody can, if you're available, can take a look and go through it so that you can have a better understanding how the training error goes down along with more iterations. So basically, as long as we run enough number of iterations, Eta Boost can perfect fit the training data. And then that brings another issue. Right? So we discussed it before, right? According to uh, uh, according to Occam's razor's principle, right? According to overfitting, right? So when we said that overfitting is always not a good sign, right? Meaning that overfitting the noises in the training data can potentially misguide your learning of hypothesis, and that was very bad generalization performance, right? And does Eta Boost have the same problem? I will see that different from most machine learning algorithms, Eta Boost suffers little about overfitting. So let us first look at the training behavior. I just want to show how the training error decreases, right? From some practical examples. So this is a training curve of Eta Boost on a typical machine learning data set. So the x-axis represents number of iterations, meaning that how many weak classifiers you have learned. Right? And y-axis just indicates the training error or empirical error. So you can see that along with more and more weak classifiers, the training error of Eta Boost decreases very fast, right? And then reaches 0. And even you learn more and more weak classifiers, the training error keeps being 0. Right? So if you look at the training error of individual weak classifiers, you see that actually they're kind of increasing. So each point in this curve just represents the particular weak classifier, the error of it predicting the training examples. But why? With more iterations or at later stages, our individual weak classifiers whose error becomes larger and larger. Right? I just want you to think about it, right? So why? I mean, the global behavior, right? The whole behavior of Eta Boost, you can see that the training error is actually decreasing very fast or exponentially fast, along with more and more weak classifiers. But for each individual weak classifier, in the later stage, its training error actually is increasing.
Is it because the way that we're weighting things is getting them farther and farther away from the original, data set?
Yeah, you hit the point, right? Very good. Right? So yeah, it's because of this weighting mechanism, right? So remember, the later the stage, right? The later means that the larger the iterations, the larger the weights for those misclassified examples, right? And you can view that the easy to classify examples, they are being correctly predicted by the previous classifiers, right? So their weights are shrinking to be really very, very small, right? And in the later stage, the remaining large weighted examples are all those hard classifiers to predict, right? So obviously, if you make wrong prediction, you get larger penalty, you get larger weight, you get larger weighted error. Right? That's intuitively why for individual weight classifiers, their errors tend to grow along with the number of iterations.
How does the alpha value change depending on the number of iterations? Like, the alpha value for H1 versus the alpha value for H2. Like in general, is there a trend of that alpha value decreasing? I would assume.
No, actually, that's a good question. Well, I guess that will depend on the applications.
Gotcha.
There's no some kind of theorem or claim about their behaviors.
Okay. So my intuition on that is that as the weights become fairly extreme and the hypotheses are being used to essentially get outliers, different values that are hard to classify with broader strokes, then they'd have more error. But I guess the alpha is based off of the weighted error, right? So not the total error.
It's based on weighted error. It's not based on total error. So it's kind of a trade-off. Obviously, you have a very large weighted training example, then so anyway, it's still based on let us look at the calculation of the weights, and that might be more clear, right? So this alpha t, so you can see the smaller the weighted error, the larger the alpha t, right? The smaller epsilon t, the larger this fractional, and then larger the alpha t. So meaning that it is kind of trade-off. It's not only accounts for the hardest training example. If you correct to predict the example who has the largest weight, but incorrect to predict all the remaining examples, that won't guarantee you a big alpha t as well.
Right. So you said that a lower weighted error.
Yeah.
Was a higher alpha.
Yeah.
Right. So, and we saw that the weighted error was increasing, and so that would mean that the alpha would be decreasing, right?
Oh yeah, yeah, of course. If the weighted, yeah, you're right. Oh yeah, you're right. Yeah, but it's kind of perturbating. Yeah. You're right.
Gotcha. And I guess that's kind of cool because like your initial predictions are, generally end up being like more heavily, like they have better votes, right? They have higher weighted votes. And so you're kind of like increasing your specificity of what you're fitting for, right? Like the ones that you keep getting wrong, but you're lowering the weight of that because you know that that's not representative of the original, like, set.
Yeah. You're right. I didn't investigate the alpha t. Yeah, but according to your analysis, yeah, you're definitely right. So if because the weighted training error is actually growing along with the number of iterations, then alpha t should have a kind of like opposite trend. Okay, any other question? Okay, great. So so this is obviously learning behavior, right? This is the most commonly used learning behavior, right? If we have like training error keep decreasing, then we expect that the error of the test, which indicates the generalization performance, is gonna decreasing at the beginning, and then at some time point it becomes increasing, right? So we need to find some appropriate number of runs where it's cutting point, right? Then we stop the training, right? We prevent our test error is going to increase, right? So that's in most practical experience of machine learning models, right? So we attribute this behavior to overfitting behavior because when you fit the data better and better, and then finally the noises will misguide your learning the hypothesis that make your test error worse and worse, right? But this doesn't apply to the Eta Boost or Boost learning algorithm. So this is a typical behavior of the Boost learning algorithm. So you can see that. So this blue line represents the training error, and the red line represents the test error, which indicates the generation performance. So you can see that even your training error goes down to zero, right? And the test error doesn't change much. Right? Sometimes it's even decreasing. That's a very interesting phenomenon of Eta Boost. So test error may decrease even after the training error has hit zero. So there is some kind of explanation provided by Shapiro and his colleagues, but there's no like theoretical theorem about this. Right? But just this is an interesting behavior about boosting algorithm. So boosting algorithm seems to be least affected by overfitting. Okay. So now we have finished the introduction of Eta Boost. So to summarize it, what is pros of Eta Boost? Right? It is simple, it's fast, and only needs one additional parameter to tune. That is the number of the iterations, right? And you can use it with any weak learning algorithm, which means because to find a weak learning algorithm is really simple, right? You just to look for classifiers that are slightly better than chance, slightly better than you just run them through a coin. Right? But there are a few disadvantages. So first, the Eta Boost, its performance depends on data set and a choice of the weak learners as well. Right? Some weak learners can give you very good performance, but some weak learners it does not give you a promising performance. So if your weak learners are too complex, Eta Boost can fail. If your weak learners are too weak, meaning that it's just very close to a random guess, it can fail as well. So the choice of weak learners may take some time as well. So empirical evidence shows that, I mean, if you don't have like too many features, like just have hundreds of features, then it's better to use like decision stumps. That is one level decision trees. You just, for each decision stump, you just select one feature to split data. And then use those decision stumps to build weak classifiers and combine them together. This is the most popular choice of the weak learners for Eta Boost. Okay, so any questions so far? Great. So let's talk about bagging methods on Thursday. See you on Thursday.
Thank you very much.
Thanks.